So today we'll see a new paradigm for algorithm design. Previously we have seen already two paradigms. One is the divide and conquer, another was prune and search. So today's paradigm will be a new one. It's called dynamic programming. Now, many of the problems come with a criterion that you optimize something. So you solve a problem, probably there exist many solutions. Among many solutions, you want to find one which is the best. And this best with respect to some metric. So this is called an optimization problem. So dynamic programming, particularly this technique, is used to solve such problems, optimization problems using this technique. So let's see first. So we'll have an example first. To elaborate on what is dynamic programming, let's take one problem so that you can understand. So this problem is called matrix chain multiplication. So let us see in matrix chain multiplication what is that problem. So we have said a 3 by 2 matrix. I am just writing down without any value in the matrix. So this is a 3 by 2 matrix. Okay. So because particularly the values are not important to me. I just want to tell you the technique. So what are there? So that's why I am just replacing them with x, some cross. 3 by 2 is multiplied suppose by a 2 by 4 matrix. Again, these values I am not putting it, any particular value, I am not putting anything. Then I have 3 by 1 matrix. Sorry, this is 4 by 1. This is a 4 by 1 matrix, and this will create a matrix which is 3 by 1. So we have to multiply these matrices and create this matrix. Now, since the matrix multiplication is associative, you can multiply these two first or these two first, then the other one. The value will remain same. So the problem is, let us see. Before I tell you the problem, let us see what happens if I multiply these two first. Suppose I multiply this one and this one, that is 3 by 2 and 2 by 4 first. Can you tell me how many multiplications you will be requiring? Count. How many multiplications you will be requiring if I do that? Yes. So that will be nothing but 3 into 2 into 4, which is 24. So you will be requiring 24 multiplications. So in this case, the problem is to minimize the number of multiplications to get the solutions. All right. So number of multiplications is the one which we are going to optimize. What is the best possible way to multiply these matrices such that the number of multiplication is minimum? And definitely that's a very valid criterion, because multiplications require some time. So inside the computer, if I can minimize the number of multiplications, that will save a lot of time. Suppose this type of multiplication is a very basic step to solve a problem, suppose. So if you can cut down the number of multiplications, that will probably save a lot of time for the original problem. So we need to know which order of multiplication matrix multiplication will minimize the number of basic multiplication, like A into B. So let's see, suppose I multiply these two first, I get something like xy plus xy, xy plus xy, xy plus xy, xy plus xy. There are 4 columns. I'll create, and basically all will be something like this. There will be 3 rows, right? It will be 3 cross 4, this one, and this will require how many? 3, as you told, 3 into 2 into 4, which is 24 multiplications. So this is 24 multiplications. Okay, still we are left with the last matrix here, which is 4 cross 1. Now I will be multiplying these two. So if I multiply these two, what do we get? We get something like this: xy z plus xy plus xyz plus xy plus xyz, probably another one will be there, xy plus xyz, and there will be 3 rows probably, right? It will be 3, actually there should be 2 dot more. So this will be 3 cross 1, and how many multiplication this last step will take? It will take 3 into 4 into 1. So there will be 12 multiplications. Now what is the total number of multiplications we performed to get the final solution? So 24 plus 12 is 36. So total 36 multiplications we used. If we do this way, this ordering, suppose if we don't do this ordering, suppose let us do the other way, which is first let us multiply this 2 by 4 and 4 by 1 first. So I am saying this. So y. So this is another ordering we are taking now. So suppose I multiply these two first. How many multiplication this will get? 2 into 4 into 1, which is 8 multiplications we are needing. Okay. Now I have to multiply this, the result of this one, with the first one. So that means we have to do this: x, that will be multiplied by whatever we got. That this will be 3 by 2, and the other one will be 2 by 1. So this multiplication will be how much? 3 into 2 into 1, which is 6. So total multiplications now, is how much? 8 plus 6, which is 14. So definitely this way, if we so definitely 14 we are getting on one place, another was 36. So you can see the way you multiply, that makes a difference. Even with this such a simple example of only this 3 by 2, 2 by 4 and 4 by 1, is making a lot of difference. One is the more than double the other. So you can imagine when the matrices are very large. Actually there are applications where matrices are very large. Matrices can be of hundreds or thousands of elements, and there the order of multiplication will matter a lot. You can see from this example, such a very trivial example, you can see that. So natural problem is, given a sequence of matrices, okay, so given a sequence of matrices, you have to come up with an ordering, or which is called the parenthesization, okay, of matrix multiplication, such that minimizes the number of multiplications over all possible parenthesization. Okay, so this is called, so what we are trying to solve, given, so this is what we are trying to solve. Given matrices A1, I'll denote it as like this: A1, A2, A3, say n matrices, parenthesize such that total number of multiplications is minimum over all possible parenthization. So let us first denote, say AI, I will denote it, its size will be, say, Pi minus 1 cross Pi. This is just a notation. Okay. So when we have been given A1, A2, A3 up to AN, so we have been given the sizes like this, we assume they are proper. So this is, say, it will be P0 cross P1, this will be P1 cross P2, it goes on, and the last one will be Pn minus 1 cross Pn. This should match. The last one of the previous one should be equal to the first one of the next one. Otherwise, you cannot multiply the matrices. So we assume they have been given like that. We are not going to check whether they are a valid sequence of matrix multiplication or not. It's assumed. Now, let us see. Suppose, how would you solve this problem? Suppose you don't know any technique, but somebody tells you that you have to solve it.
Find out the highest column in a total matrices, which is the largest number of rows or columns.
Right.
Perform that multiplication first, then go for the second one.
But I am not. If you tell me such a solution, I will not accept it, because you have to prove it to me that it is the highest. You are saying something, but why should somebody believe? And probably it is not true.
The largest number shouldn't be multiplied twice.
Yeah, but that does not mean, because once you take this strategy, I am sure I can come up with an example after a little bit of thought that something else will be better. It's not that simple, that the highest number one will give you, because once you take an action, that may affect your action later. Remember that you have to look into the future. Once you have multiplied something, that is going to be multiplied with something else later, and we are not looking at the values of the elements at all. So now suppose we don't want to do any tricks, a very naive way we want to solve it. What we can do, we can generate probably all parenthesization possible. Suppose we generate all parenthesization possible, and then count the number of multiplication, take the minimum. That's anybody will do who doesn't know anything about probably the algorithm technique. Okay. So suppose we do it naive way, then let us see what is the difficulty. Why people should not try to do something like this. The difficulty is the total number of parenthesization of given n matrices is too large. You cannot even hope to generate all the parenthesization possible when, say, n is equal to 30 or 40. So let us see, because this is a combinatorial problem. What is the combinatorial problem? So given it n matrices, we want to know what is the total number of parenthesization, different parenthesization possible with this. So this problem, so let me just take an example, say x, these are matrices, x, okay, here I'm showing one parenthesization. So these are the matrices. So it means this will be multiplied, this will be multiplied, then the result will be multiplied, then this will be multiplied, then the result of this will be multiplied with this. That's the meaning of parenthesization. Okay, that's the usual meaning of what parentheses generally mean. Okay. Now corresponding to one parenthesization, we can always build a tree, a binary tree. Okay. So the rule of the binary tree is this: every interior, okay, what we are doing now is just trying to count what is the total number of parenthesization given n matrices possible. Just a combinatorial bound on it. We want to know how good it is. Every interior node corresponds to a pair AB. Okay, and we'll denote the open parenthesis and right parenthesis as AB, A and B, two symbols. The string, I'll tell you what I'm writing now. The string of the left subtree is nested inside the string of the right subtree follows after B. Okay, let us see. So suppose I want to build a tree for this one. The tree will be basically this. I am drawing it upside down. So this is a leaf. So if you follow this rule, what we are doing, every node, first of all this node represents the parenthesization of outermost parenthesization. So the left subtree, so this is the left now. I'm just drawing it in the upside down position. So this is the left. So left subtree will contain the string for the left part in a nested manner. Okay, so you can see like this entire thing goes here, and the right part is just symbolizing this matrix here. There is nothing here. Okay. So like this node, it is breaking up this entire thing into two parts. This part is one part, this is one part. Now this one part goes to this left subtree, and for this one is just coming as a leaf because there is no parenthesization here. So now if you look into this one is breaking into two parts. One is this part, another is this part. So there are two nodes. It goes on. Okay. Now I am converting this entire tree into a string, and the string is formed as I have told it here. Each node is representing one pair AB, which is basically one parenthesization. So if I do this conversion now, you will get the string like A. You verify later. B A B B A B B. So it's like this. So this is matched with this. These two are matched. Then this will be matched with this. Then these two are matched. Then this is matched with this. Then these two are matched. Okay. If we follow this rule, we will get exactly this string. So each node is representing a pair AB. Okay, and the left part, the string of the left subtree is nested inside. So this AB will have the left part, left subtree, whatever left subtree represent, that will be nested inside, and anything on the right will follow this B. But in this case, there is nothing. There is no internal node, so it's not following anything. This B. That's the rule this one is saying, how to create this string from here. You could have also created this entire string very easily. Just take A for left, B for right. Basically, you will get another string, which is a little bit different from this one, but it is almost similar. So entire parenthesization I can always represent as a string of AB. Okay. And this AB is a very well formed string. Means not every sequence of AB you can represent which has a parenthesization, corresponding parenthesization. You cannot. Like suppose I have a string say BBA, that does not exist a parenthesization for this string. So those strings which has a valid parenthesization corresponding to it are called well formed strings. So let us see. First of all, how many letters will be there? AB, roughly order of n. If there are n matrices, the total number of parentheses will be order of n. Actually, it is exactly n plus 1 or n minus 1, something like that. It is not more than that. So, total number here is n, roughly n, order of n. So, we want to see how many strings, say let us see the total number of symbol is say n, how many strings are possible with symbols a, b, where total number is n such that each string is well formed. That will correspond to a parenthesization, there is a one-to-one correspondence then. So, we want to count how many well formed strings can be formed with n, say total number of n a and b, where a and b are equal, definitely they have to be equal. So, we want to count that. Let us see, that will tell us that totally how many parenthesization, different parenthesizations are possible. So, I will just claim this. Our claim is there are 1 over n, 2n minus 2n minus 1 different parenthesization of n matrices. Okay. So, suppose there are n matrices, you just counting the total number of different such strings, you can always prove that this many different parenthesizations are possible. Let me not go into the details of proving this. This is sometimes called also Catalan number. Okay, this is called Catalan. You should know these terms, Catalan numbers. Basically, this quantity comes into combinatorics of many other things. What is the total number of different binary trees you can have with n nodes? Again, these things come. This particular formula comes into picture. Okay. So, but what is important now? What is this order of this guy? 2n minus 2, choose n minus 1, 1 over n. I do not want to know exactly, but can you see that it is something like some constant over some n will be there, something roughly is exponential. It is roughly exponential. You find it out. Why? Because this is 2n minus 2, 2n choose n, roughly you can take it as 2n choose n. 2n choose n will give you something n to the power n, something like that it will give you, right? So, I'm not calculating exactly. Suppose we take 2n choose n, roughly it will give what, like 2n minus 1, it goes up to how many terms, 2n minus n plus 1, something like that. So, roughly there will be n terms, they are all multiplied. So, each one n to the power n. So, this is roughly n to the power n, and you are just dividing by another n. So roughly I can say 10 to the power n minus 1, roughly I am saying roughly. So, this is very large. Here I said some constant to the power n, but actually it is n to the power n. This is Stirling formula, if you do you will get it. Again this Stirling formula will give you something n to the power n half. The entire point is exponential. I do not want to know exactly what is the exponent in this case. So, if you try to count if you try to create all the possible parenthesization, that is going to be hopeless. That is which is important for us to know. Even if it is n to the power n half for n to say n is equal to say 10, that becomes 10 to the power 5, which is okay, bearable. Take 20 to the power 10, no way. 20 to the power 10, if that many numbers you have to generate, it will take years after years. Probably you will never finish it. So this is the difficulty of doing it in a naive manner. We cannot hope to generate all parenthesization and solve it. And this is the case actually for solving most of the optimization problems. You cannot create all the cases then choose the best one, because the total number of cases is too large. So, we have to come up with something such that we do not generate all the possible cases. So, let us see. We will first do a very naive solution again, but a little bit more carefully, more algorithmically, and we will modify that algorithm later. So, Let us see. Suppose I denote Mij is equal to the minimum number of multiplications needed for this ai to say aj. So I took the subsequence ai to aj. This is a subsequence in the given total matrix sequence. So suppose multiplying between aij, the total number of multiplication is mij, suppose. All right. And also we assume an array A, this is an array, or let us assume P, so that we don't get confused with this A. So this P, it goes from 0 to n, where ai has size pi minus 1 cross pi. Sorry, I should not say pi here, because the way I am now, it is an array, so I should put pi minus 1 cross pi, right? So a1 will be basically p0 cross p1. So this array has been given. So what is the input to your algorithm? Input to your algorithm is not this entire matrices, only this array P. If the array P is given to you, you know implicitly these matrices are of this size. If you know this is the meaning of it. So that's the input to your algorithm. Now you have to come up with your parenthesization. So let us see. We assume that P is global. So I am going to write a function under this assumption. So function mij, this function will be called recursively. It returns, what does it mean? It returns the minimum number of multiplications required to multiply in the sequence from ai to aj. It returns, this function returns that mij, basically small mij returns. So how do you do? So if I is equal to j, then what? Then return n is equal to 0. There is no multiplication. If I is equal to j, basically no multiplication is required. It's the same matrix which is there. There are no two matrices have been given. This is the boundary condition. Else we set a very minimum value which is initially plus infinity. Very high value. Actually, this will get decreased. So you put a very high value here, which you don't expect to be there normally coming into the algorithm. So minimum is equal to plus infinity. For next, what we are going to do is a very naive way again. Between I and j, we run another index k. Between I and j, we are seeing all possible parenthesization. Okay. So this is this loop doing k is equal to I to j minus 1 do mult is equal to, you call this matrix mij again with the parameter mik, and again another call mk plus 1 j plus, I'll tell you why we are doing this, pi plus minus 1 pk pj. Yes, just let me write it, I'll tell you. Then min is equal to mult and if and for, let me write it first, and if. Okay, so what I wrote is this: if I is equal to j, then return m is equal to 0. Else minimum is infinity. You just set it up. because this will get decreased in the algorithm. What we are doing for k is from I to j minus 1, what we are doing, look at I and j. So this is ai and aj is here. What this loop is trying to do, trying to put k here, k next one, k next, so it is trying to take parenthesization like this first, then the next parenthesization like this and the rest, then the next one is this and the rest, and within the each one it's assuming that have been multiplied with minimum number, because you are giving recursive calls. So this variable k is running from I to j minus 1, is taking all possible parenthesization between I and j, that's what it is doing. So a generic step is what, your k is here, so you are multiplying between I and k, so you are giving a call mik, which will return you the minimum number of multiplication to multiply ai and ak. Then it is calling for k plus 1 to j, that's what it is, this one mk plus 1 and j, it will return the minimum number of multiplication to multiply between ak and aj. Suppose k is the one you have taken, then after you have got back these two multiplication, you have to multiply the two results to get the final solution for I and j. So that multiplication will take this much, pi minus 1, pk and pj. Okay, that's what we are doing here. So now this is the total number of minimum multiplication if k was here, if this aij was partition at this point k. Now in the original aij minimum multiplication, k have been put in some place between aij, I don't know where. So we are testing for all possible position of k and calculating this total number of multiplication for all possible values of k, and then checking every time which is the minimum among all of them. The minimum among all of them will give you the global minimum for multiplying ai and aj, between ai and aj. Did you understand this step? This step is very crucial to understand the dynamic programming. If you don't understand this step, you cannot follow anything else later. Pictorially, did you understand what I said? Okay, so you want to know why this one is there. Okay, first of all, suppose k is here between ai and aj, somewhere we have to parenthesize. It has been broken somewhere, we don't know. Suppose there is a minimum multiplication, that minimum multiplication has broken it up in some place, say let that is the place is k. Now that one has a minimum multiplication between ai and ak, that is given by this recursive call. Then k plus 1 and j, that is given by this recursive call. Now once you get back the solution of this multiplication and this multiplication, you have to multiply these two. So sorry, add these two. No, first you have to multiply these two matrices. Okay, so for that one, how many multiplication you would require is exactly pi minus 1, because this one will be of size pi minus 1 pk and this one will be pk pj. So what is the total number of multiplication for multiplying these two results is pi minus 1 star pk plus star pj. That's what this quantity. So what you are getting, you are just checking, if I place the k somewhere here, what is the total number of multiplication I will require, assuming that the nested ones have been multiplied in a minimal sense, that is this mult. Now you are checking all possible values of k between I and j, because you are sure that the minimum one, the global minimum between I and j has taken some value of k, you don't know which one, but you are checking all possible, and that one, that mult will give you the global minimum. You are checking, you are not excluding any possibility, and that's why if mult is less than mean, you are setting that mean is equal to mult. Okay, so and sorry, actually I forgot to return something. So basically you should return mij m is equal to mean. After, sorry, if you do this after n for here, you should return m is equal to mean. I did not return anything. Technically you have to return something. I did not return something. Okay, so this is the essence of the algorithm, what it is doing. So here again we are checking all possibilities, but in a very regular way. It's not that we are generating haphazardly and checking, in a very recursive manner. But let's see how much time does this take. Did you understand this entire algorithm? It's very crucial to understand the next one. Okay, once you have understood, let us just see how much time does it take. And you can, what do you think? What should it be the case? What is your guess? This algorithm is bad or good? Pretty bad, because it's taking all, essentially it's taking all parenthesization. See, it cannot be very good. It's pretty bad. Okay, so anyway, let us just see what is the analysis. So if I analyze this, then I should get Tn. Can you tell me what should be the right hand side? Now you should know this. Tn summation, yes, very good, summation over k. K is going from 1 to n minus 1 is giving tk, another t n minus k, right? These are two recursive calls and doing it for all k's. That's why k 1 to n minus 1, right? So this is the entire thing plus order of n. So this is our recursion. Definitely t of 1 you can put, because there is a I is equal to j, there was a terminating condition. So if t is equal to t1 of 1, you can put some order of 1, some constant. Okay. So now if you try to solve it, I don't want to solve it here exactly. You can go back and solve. We can write Tn a little bit, simplify it. So I can write this is equal to 2k goes from 1 to n minus 1 tk plus order of n. Okay. So suppose you do this, you can solve it. Okay, try to solve it. But let us, I just don't want to solve it very exactly here. But let us have an estimate how bad it is. I can always say that Tn is greater than equal to u of n, where u of n I can define it as 2 of u n minus 1 plus 1. Can I say that? Can you see why I can say Tn is greater than un? See, what I can take, there is a summation k is equal to 1 to n minus 1. I'm just taking the last term Tn minus 1. So I can always say Tn must be greater than equal to 2 Tn minus 1 plus order of n. Order of n I have replaced by order of 1 actually. So this is a very sub estimate. It's a very bad estimate, but we'll see how it is greater than equal to, not less than equal to. So instead of taking all the terms, I have taken only the last term. I have replaced order n by order 1. So Tn must be greater than this thing. But even this function un, where I have discarded so much, is so bad that we cannot hope for a good solution, because this will give you something like 2 to the power n. Something like this roughly. Because 2 un minus 1 give you another 2. There will be n multiplication of 2's, so that will give you 2 to the power n. So even this function is giving 2 to the power n, and Tn is much actually it is much larger than un. So you can see Tn is so bad. You can see that Tn is very bad. So this algorithm what we did is pretty bad in terms of time complexity. But let us see, suppose what we are doing in if I represent this entire thing pictorially, we had a call with n elements. These n elements gave how many calls? Each recursion, if I represent it like this, a tree, a node in the tree, this call gave some n number of calls almost, right? Because for different values of k you gave 2 calls. So lots of calls you gave. So probably this one has smaller size now, but lots of calls you gave. Now this one again gave lots of calls. This one gave another lots of sub calls. So each one is starting new calls, lots of new calls, and actually those are piling up and giving you a explosion. This is called the combinatorial explosion. Every time you are multiplying with something, this one gave say 3 calls, this one gave another 3 calls. So every time it is getting multiplied. But see what is the redundancy here? There is a redundancy. Can somebody tell me what is the redundancy? We are doing something again and again unnecessarily.
So if we have found that number of multiplications till now has far exceeded the minimum we have got, we can just stop the process.
Right, that is one thing. What he is saying is, suppose we keep this minimum as a global minimum, and some call has given that it is more than the minimum, we should stop. It's like a prune and search in this tree. Okay, but beyond that, even that will not save you a lot. Even if you do that, I can still show that it is remaining exponential.
So we are checking for a particular
Parenthesization, yes.
parenthesization again and again.
Right. So he has pointed out the right thing. What we are doing, one particular, so go to the lower level. So let us go back to the lower level. Like suppose I have this matrix. So let us look into this matrix multiplication, this 2. Now this 2 multiplication is getting generated by several recursive calls. Like one parenthesization which is using this ultimately will require this, another parenthesization with this will require this, another parenthesization with this will require this. Now this multiplication, and we are calculating it again and again, and that's the loss we are doing. If we are careful enough, why should we calculate again and again something? We keep it somewhere. We keep it somewhere. And that is the crux of the entire dynamic programming. So dynamic programming, what it will do, instead of calculating this one again and again, it will maintain one array or a table where it will keep its value. So this is called the bookkeeping. So with that bookkeeping, it will keep the value which it has already calculated, and then it will use it for later purpose. And that will save us a lot of time. We will see in the next lecture that if we do this, suddenly what will happen, this entire algorithm, instead of remaining exponential, will become polynomial. So we will have for the same problem, we will have a polynomial time algorithm. What is a polynomial time algorithm? Again, I can express the complexity as some n to the power c, where c is some constant. Right now we have something like n to the power n or c to the power n. Suddenly this will go to n to the power c, not c to the power n. And we will see that just by doing that bookkeeping, we can save a lot of time, even a lot of space. You can see all these recursions recursion will take a lot of space also. Everybody will generate its own recursion. This entire recursion tree has to be maintained somewhere. So that will take a lot of space also. So all this will be saved by doing this simple bookkeeping, and that is what is done by dynamic programming. So that we will see in the next lecture.